Okay, welcome to this afternoon section. The first speaker is Professor Karel Dekimpe for his fourth lecture about Post Lie algebras.
Okay, thank you very much. So, welcome to everybody who keeps coming. Thank you for this. So, let me recall a little bit what's the situation. So, we have been studying the existence or non-existence of Post Lie structures on several pairs of Gn. So, we first considered the case when n was abelian, and then we got the fact that, well, such structures do not exist if G is simple or semisimple. Yeah. So remember, this was the case of left-symmetric structures. So left-symmetric structures certainly do not exist in simple or semi-simple Lie algebras G. And then we studied abelian and nilpotent G and considered all possible cases. And in fact, the result was, if G is abelian or nilpotent, then certainly it cannot be simple, semi-simple, or reductive, the n. And so n had to be solvable, and for the abelian case, we proved that it had to be two-step solvable of derived length 2. So to start with today, I will consider the case when G is solvable and see what's possible over here. So up till now, we have had no success with pairs Gn, where n was simple, semi-simple, or reductive, except for the trivial cases when n is equal to G. So let me now consider the line where G is solvable. So this was part D. So G is solvable. And before I start treating really the case that G is solvable, I actually want to mention a general technique for constructing pairs Gn admitting a Post Lie structure. So I want to introduce a general technique which is quite useful to construct examples of pairs of Lie algebras Gn admitting a Post Lie structure. And the start of this technique is to start with a Lie algebra n. So, let n be a Lie algebra. And assume that you can write n as a direct sum, let's say, of A plus B. So direct sum of two vector spaces, such that these vector spaces are also subalgebras. So such that A and B are subalgebras of n. So I do not mean that n is the direct sum of Lie algebras A and B. They do not have to be ideals in my Lie algebra n. They just have to be subalgebras. But I do want the sum to be a direct sum of vector spaces. Now we define a new bracket. On n, so it is as a vector space, just this. And actually, the new bracket is just define a bracket as if it were the direct product of the two subalgebras. So we define, let's say, if you take an element a plus b, an A over here, a B over there, and then a prime plus a B prime. Also, if A and B, then I define it as the sum of A with A prime. I also take B and B prime. And normally, to take the direct sum, I would take a plus sign over here, but it turns out to be convenient to consider the bracket where I put a minus sign over there. Okay, so this is not the bracket in n, because if I would take the bracket in n, I would also have the parts bracket BA prime and bracket AB prime as part of the bracket. So I forget about the mixed terms, so I consider only the bracket with the terms of A and the terms of B to consider this new Lie algebra. And in fact, let's say call the G with the bracket, yeah, the new vector space with this product. Well, this is a Lie algebra. Which is isomorphic to the direct sum Lie algebra A plus B, of course, by the map, let's say phi from G to A plus B, sending an element of the form A plus B to the element A minus B. If you take this linear map, yeah, then you'll see that the Lie algebra with this bracket, or let's say the algebra with this bracket, is isomorphic to this Lie algebra, and hence it has to be a Lie algebra itself. Yeah. Okay, and so from n, we construct a new Lie algebra, and now I have a very nice technique to define a post Lie structure on this pair. So, definition. Yeah. Let's say for x equal to A plus B and n, which is equal to G, and also y equal to A prime plus B prime, also an element of this vector space, we define x dot y as being minus the bracket of B comma A prime plus B prime. So I define this as a product. So from the x part, I do not need the A, I only use B, and I define this product. And of course, this is a bilinear product. This is easy to see. And I claim now that this is a post Lie structure on the pair Gn. So let me prove this. So proposition. With n, G, and this dot product as above, we have that dot is a post Lie structure, post Lie algebra structure on the pair Gn. And so to prove this, we have to prove the three equations that has to be satisfied for a post Lie structure. So the first equation says that is it true that xy is the same as x dot y minus y dot x. So I will check if this holds. Now this is just a computation. Take x to be equal to A plus B, y to be equal to A prime plus B prime. Of course, small a's are the Lie algebra A and small p's are the Lie algebra B. Then I have that the bracket of x and y is by definition the bracket of a prime minus b prime. So this is the left-hand side of the equation. The right-hand side becomes x dot y minus y dot x, which is minus, so by definition, b a prime plus b prime, and then minus yb becomes plus b prime a plus b, and now since this is bilinear, this is the same as minus b a prime yeah, of course I'm wrong. This I need this to be xy minus brackets. So the left hand side, excuse me, is a little bit more complicated. Okay. So the left hand side is this one, a prime minus b prime, and then minus a plus b a prime plus b prime. So I forgot to have this term. So let me compute further now the right hand side of the equation. So I get b a prime minus b prime plus b prime a plus b prime b. Now I have to work out a little bit further on the left hand side. So the left hand side is, well, let me this I already had, and then the full bracket and n, so this is minus a prime minus a b prime minus b a prime minus b prime. Okay, so let me have a look. First of all, I can cancel at the right hand side the two factors with a and a prime. Okay. And now let me look for comparison. So I get here b prime b with a plus sign. Well, I do not see anything with a plus sign, but of course I have b prime with a minus sign, which is the same as b prime b with a plus sign. So these guys are already equal. Okay. Then let's say b prime a with a plus sign is the same as e b prime with a minus sign. So this is this part. And then minus b prime, I find this one over here. And then finally, minus b a prime, I find over here. And then I see that, yes, condition 1 is really satisfied. This is okay. So part 1 for a Post Lie structure has been verified. Second part, now I'll try not to make a mistake. So the second part says that xy times z should be the same as x times y times z minus y times x times z. Again, I let x be equal to a plus b, y be equal to a prime plus b prime, and for z I will not need to write it as a double prime plus b double prime. That won't be necessary. Okay, so the left hand side, let's make a computation. So the square bracket is a A prime minus B prime like this, and this has to act on Z, so I have to multiply this with Z. So remember the definition, x dot y is take minus the bracket of B with this element. So I have to take the B factor in this term, which is this one, then put a minus sign in front, so I have to think about this minus sign, and I can just write this as this B prime, comma, Z. So this is the left-hand side of this product. Let me now work on the right-hand side of the equation. So the right-hand side, so this is this part, so this means this is A plus B times Y times Z, and I know that Y times Z is minus B prime Z, by definition of the product, and then the other one is minus A prime plus B prime, this is the Y. Yeah, and then I have to take the product of X and Z, so this gives me another minus sign, and I have to take B acting on the second component. Okay. And now again, I use the definition of the product, so the minus sign will vanish. I get B prime Z plus, well, now I have to use a minus sign, minus the bracket of B prime BZ. Yeah. And now I can slightly change this factor. So this is B prime Z plus B prime Z B like this. And now I can use Jacobi identity. So I see B prime Z, B prime Z. So if I add the other one, circular permutation, I get 0, or this is minus the one in which Z is in front, minus Z, and then B prime. So by Jacobi identity, I get this. And of course, this side is the same as this side. So this means that, okay, condition 2 is also satisfied. And this is mainly by using Jacobi identity for the original bracket of N. And then finally, I also want to do this computation. Is checking the last condition. Last condition says that left multiplications are derivations of N. So the third condition that has to be satisfied is that X dot YZ should be the same as X dot Y comma Z plus Y X dot Z. Okay, again, as usual, I write X as A plus B. I will not need this for the Y and the Z because they do not appear on the left-hand side of the multiplication, so I can just leave them as they are. So this one gives me the left-hand side is minus the bracket of B YZ, and the right-hand side, this is, okay, the bracket of this guy. So this is the multiplication of minus BI comma Z, and then plus this one, well, this will also be minus then, minus Y, the bracket of B comma Z. Yeah. Okay, and again, I have 3 terms, yeah, 3 times triple bracket b by z, b by z, b by z. And now you can easily check that by the Jacobi identity, these two guys have to be equal. And so we are done. Yeah? This means that also the third condition is satisfied. And so using this technique, we do have a Post Lie structure on a pair Gn, where now the combinations can be quite surprising or quite complicated. And I want to use this in a few examples now, this technique. Yeah. So it is often possible to write a Lie algebra as a direct sum of two subalgebras. Yeah. For example, let n be, let's say, SLN C, or SLN of any field you like. Yeah. Then elements of n, yeah, are matrices, yeah, with trace 0. And then I can look at, let's say, for example, you take A to be the Lie algebra consisting of all lower triangular matrices. Yeah, so this is shorthand to say just I take A to be the subspace of all lower triangular matrices. I take B to be the subspace of all upper triangular matrices, of course, with trace equal to 0. Okay. And then we see that the Lie algebra G we get in this way. As I said, this one is isomorphic to the direct sum of the two Lie algebras A plus B. This is, of course, a subalgebra. This is a subalgebra. Yeah, and it's quite obvious that this space as a vector space is a direct sum of the two. So I can apply the construction. Now, the algebra A, this is lower triangular matrices. This is, of course, a nilpotent one. It consists entirely of nilpotent matrices, so this is already enough. The B is a solvable one. Yeah, if you take the right one, you get upper triangular with zeros on diagonal, and this is nilpotent, so this is okay. So this guy is solvable, non-nilpotent. Maybe let me add this. And so this means that this Lie algebra is solvable plus non-nilpotent. And we do have, by the construction, there is a Post Lie structure, which I can write easily, very concrete, on the pair G comma N, which is SLN. Okay. And so I see that I do have a possibility for the situation that G is solvable and N is simple. So this situation now occurs. Yeah? While in the nilpotent case, this was really impossible. If I have a nilpotent Lie algebra over here, this one had to be solvable. So the moment we go to solvable, simple is also allowed. And of course, going from simple to semi-simple is not a problem. Yeah, we also have that we have then the direct product structure. For example, on G plus C, G and this one, or you do the same for different ends or whatever you like. So you can always consider this. This is also solvable non-nilpotent. So I also have examples where the group, the Lie algebra is semi-simple. Yeah. And for reductive ones, well, for example, if I do the same technique over here, but I replace n by GLN C. And I just take B, all the upper triangular matrices, and I get the same step. So I get a Post Lie structure also on another solvable one, let's say G prime, GLN C. Okay? One dimensional bigger than this one. So this means that more or less everything is possible. Simple, semi-simple, reductive. So let me add this to the scheme. So if G is possible, then there are examples of solvable Lie algebras G's and simple Lie algebras N admitting a Post Lie structure. The same holds for semi-simple and the same holds for reductive. What about this case? Solvable G and nilpotent N. Well, this is actually again easy to construct. Using the direct product situation, I can take a direct product of one of this form, G solvable and nilpotent, and here G nilpotent and solvable. If I take direct product structure of those two, I get one fitting over here. And so, as a conclusion, we see that if G is solvable, well, there are Post Lie structures possible, in all possible types of algebraic properties that I mentioned over here. So this is a very less restrictive situation than abelian and nilpotent. Okay, I want to mention a few more remarks. Namely, I gave here an example, just one example of a simple Lie algebra admitting a solvable Lie algebra and then structure and then a Post Lie structure. This can be done for any choice of simple or semi-simple or reductive Lie algebra. You can always find some solvable Lie algebra which is non-nilpotent, such that the double or the pair admits a Post Lie structure. So all possible simple, semi-simple or reductive Lie algebras do appear in this list. So this is also nice to know. Okay, so the solvable case has now been completely solved by this. So it's time to move on. And the next situation is a situation for simple Lie algebras, but actually I will treat simple and semi-simple a little bit together because I can use some techniques for both of them. So for E is, what if G is simple or semi-simple and not simple? Well, the first thing I need to solve this case is a lemma, which can also be useful in totally other contexts. So let G be a semi-simple Lie algebra and M a G module. So you have already seen this week what is meant with the G module. I think also Professor Wagemans said that you have an action of your Lie algebra on elements of M that has to satisfy this rule. But actually I prefer not to use the dot, because for me the dot comes from the Post Lie structure and I do not want to to get distracted and to get confused about what is the exact meaning. So I often want to be a little bit more detailed in my description. So I said the G module, this means that I have a map rho from G to the endomorphisms of M, just that this rho is a Lie algebra morphism. And so this means that exactly the same. If you let this act on M, it should be the same as rho of X acting on a rho of Y acting on M minus this thing. And of course, we have seen examples of this. If you have a Post Lie structure on Gn, yeah, then we have seen that the left multiplication, that this acting, let's say, on Z is the same as L of X of L of Y acting on Z minus L of Y L of S acting on Z, which, if you write it just in the shorthand notation, was exactly this thing. So for any Post Lie structure, N is a G module. And there's something more, it acts using not only endomorphisms of N, but using derivations. But not to get confused between the general action and the Post Lie structure, I will use the rule instead for my model structure. Okay, and now the lemma I want to use is the following. If G is semi-simple and M is a G module with the dimension of M less than or equal to the dimension of G, then for all elements M in the module M, it holds that the annihilator of the element M. So this is the set of all X in G such that rho of X acting on M is 0, then this is a non-empty space, is non-zero space. Okay? So the annihilator is never trivial for whatever M you take, as long as the dimension of your module is not bigger than the dimension of the Lie algebra. So let me prove this. And actually, the way I'm going to prove this is applying the theory of left symmetric structures, what we already have. So I will use my own Post Lie theory to prove this lemma. So you can see this as an application of what we have done up till now. Okay, so we have this situation. We fix an M in our module M, and we take the map side, which goes from G to M, and which sends X to rho of X times M. Yeah, and then of course psi is a linear map from this vector space to this vector space, and the kernel of psi. This is exactly the elements X such that this is 0. So this is really this annihilator. So the annihilator is the kernel of this psi, and I have to prove that this kernel is never the 0 space. Well, one thing is clear: if the dimension of M is less than the dimension of G, well, then you can never have an injective map from G to M. So this means that the kernel of psi is non-trivial, and we are done in this case. So suppose that we are in the situation that the dimension of M equals the dimension of G, cannot be bigger because we have this assumption, okay? And that the kernel of psi is 0. Then I should reach a contradiction. So this is but I suppose, and this should not happen. It should happen that also in this case the kernel is non-trivial. Okay, so if this kernel is trivial, this means that this map is injective, and since they have the same dimension, this means that psi is not isomorphism of vector spaces. So we have that psi is an isomorphism of vector spaces. Now I will define a product on G, a bilinear product on G using this psi. So define now the product dot on G as follows. So I will use both the rho and the psi to define this product. So take x and y in G. So what I can do is I start in G and I have the element y. Then I can use psi to go to M. So I get here psi of y. Then I can apply the map rho of x. This is a map sending an element of M to another element of M. So this is rho of x applied to psi of y. And then I can go back to G using the inverse map. It's an isomorphism. So I get psi minus 1 of rho of x of psi of y. Yeah. The psi of y is just rho of y. So this is by definition rho of y applied to M. Yeah. Here is the definition. Yeah. So I will use this scheme, and so I define the product x dot y as being psi minus 1 of rho of x of psi of y. And now the claim is this dot is what we call a left-symmetric structure on the Lie algebra G. And if I can prove this, we are done. Why? Well, remember, left-symmetric structures, these are the post Lie structures in which n is abelian. Yeah? And for abelian n, there are no possibilities to have a post Lie structure on pair Gn or left-symmetric structure when G is simple or semisimple. Yeah? So if I get this, yeah, if I can prove this, I get the contradiction because there are no left-symmetric structures on semisimple Lie algebras. Okay, let me do this. So I will do this as follows. What I do have to check, there are two conditions. So condition 1 is that x comma y is the same as x dot y minus y dot x. And the second one is that x dot y dot z is the same as x dot y dot c minus y dot x dot c. Okay, I will check for you the first one. The second one is very analogous, and you can do this as an exercise. So let us check one. Yeah. And actually, since psi is an isomorphism, I will check that psi of xy is the same as psi of x dot y minus psi of y dot x. Now, what is psi of xy? By definition, this is rho of xy applied to M. Now, the question is this guy equal to psi of x dot y? Now, x dot y has been written over here. So this is rho of x of psi of y, apply psi to this side. and then vice versa, interchange y and x, so this is rho of x times psi of x, and of course, now apply again the definition of psi minus rho of y, rho of x dot m. And as you now can see, this is just saying that rho is the map defined in the modular structure of G of n. So we have that rho of xy is the same as rho of x times rho of y minus the other one. So indeed, this is okay. And so we have checked condition 1. Condition 2 is really more or less the same. So I leave this to you. And so we can conclude that we have a contradiction. Yeah, so this means that the kernel of psi is really also non-trivial in this case, and we are done. Okay. So this annihilator is always different from 0 as long as the dimension of the module is not bigger than the dimension of G. Okay, and now I'm going to use this lemma in the proof of the next result, saying something about Post Lie structures in case G is simple or semi-simple. So the result is as follows. Let me call this theorem. Then Gn be a pair of Lie algebras such that G is semi-simple. Just I also lie now with the word semi-simple, the word simple. Now, if the pair Gn admits a Post Lie structure, then n is not solvable. So when G is simple or semi-simple, then the Lie algebra n cannot be solvable. So not abelian, not nilpotent, not solvable. So these cases are excluded. Okay, and to prove this, I will need the previous lemma at a certain moment. So proof. So let us assume that n is solvable. And so we should reach a contradiction again. Now, the fact that we have a Post Lie structure, we can interpret this as there is a Lie algebra map, a Lie algebra morphism, from G to n semi-direct derivations of n, sending x to x, comma L of x, linear multiplication by x. So this was another possible way to say that we have Post Lie structure. Yeah. And now there is natural map. Well, no. Let's say take. Let's say S to be L of G. Yeah. So all the L of x for which x belongs to G. So what is S? S is actually the same as P of G. If you view this as an injective map, so you see G as a subalgebra of this whole algebra, where P is projection onto the second component. Okay. But now G intersect N. So if we view G as a subalgebra over here, just the algebra consisting of the elements x comma L of x, well, this has to be 0. Why? Well, this guy is solvable, and I assume that this one is semisimple, so it does not have a radical. The radical is 0, so it does not have any solvable ideals. This is solvable, and so this would be a solvable ideal in my Lie algebra G, which is impossible. So this would be the kernel of this map. Yeah, so it has to be trivial. Yeah. So therefore, S is the same, is isomorphic to G. Yeah. So this, the P restricted to G is an isomorphism onto S. And so this S I chose this. Yeah. So this is also semisimple. Okay. And moreover, we have that N semi-direct S will be the same as N plus G. And actually, I can write equally well that this is a split extension of this form. Okay. So to see how this is done, remember the class of yesterday when I introduced this H. This is exactly the same proof to see this equality. Now, this guy is solvable. This guy is semi-simple. The same over here. So this means that this N is really the radical of the Lie algebra N semi-direct S or N semi-direct G, and both S and G, yeah, are what is called Levi subalgebras of this algebra. So both S and G are what is called Levi subalgebras and semi-direct S or N semi-direct G. And then there is a theorem, the Levi-Malchev theorem, says that there exists the Z in actually the nil radical of this algebra. So let me call it nil radical of this algebra, such that G is the same as, if take the exponential of the adjoint of G. I will explain a little bit later what all of this is, and you apply this to the algebra S. So this is a well-known theorem that I'm going to use. So the adjoint of G in a Lie algebra is, of course, nothing else than taking the bracket of G with something. So this is the adjoint map. Yeah. This is, I guess, well known. What's the exponential of the adjoint of G? Well, you take the power series for the exponential map. So you take the map from n to plus infinity of the adjoint to the power n, subdivided by n faculty, and you apply this to an element. So this is how this map works. Okay? And so we will have this part. Now, what does this mean? Okay? Well, so take an element of S. So S, this is everything I can get, all the, let's say, left multiplication maps from G. So such an element, say, this is of the form Lx, and so you should see this as 0Lx if you see it in semi-direct S. Z, this is an element of the nil radical of n semi-direct S. So it's certainly sitting inside the radical, so it's certainly an element of Z. So actually Z, you should see this as Z, and then having no part in the S side. Okay. And now what is the adjoint of Z acting on this Lx? So this is actually taking the bracket of Z0, 0 Lx, in this semi-direct product over here. And remember, semi-direct product, this means I take the bracket of this one with this one, so Z0 is 0. Then I let act this one on this one, minus this one on this one, so I get minus Lx acting on Z. And then the second component, the bracket of 0 and Lx, so the second component is just minus, is just 0. Okay. So this is what this map does on an element of S. Remember, I will have to look at powers of this. Now, how are we going to use this? Well, we have this Post Lie structure. So recall, N is a G module via the map L. So we have L going from G to the endomorphisms of N. Actually, we end up at the derivations, sending X to L of X. So N is a G module, and we know that the dimension of N is the same as the dimension of G. Okay. So what we do have is that for this fixed Z, okay, so fixed M equal to Z, then we know by the previous lemma that the annihilator of M, so the annihilator of Z is non-zero. So this means that there exists some X in G, which is X non-zero, such that L of X times Z is 0. And so this implies that the adjoint map of set on L of X is minus this term, that this is 0. So at least for one X, we have that this is 0. And then, of course, we have that for all n bigger than 1, we have that the adjoint of n of set applied to Lx has to be 0. Yeah. And then if we look at the exponential map, so this means that the exponential map of the adjoint of Lx, yeah, that this has to be, well, if you start with 0, you just get the identity map. So this starts with Lx and then plus the terms from 1 to infinity, but this is 0. So this is 0. Okay. And now what does this help us? Yeah. So this shows that Lx is an S, and by the Lévy-Malchev theorem, we know that G equals exponential map of at Z applied to S. So this, it follows that the exponential map of at set applied to L of X should be an element of G. But this is just Lx, yeah, which we should see as 0 Lx and n semi-direct S. But this is now a contradiction because elements in G These are all of the form Ly, Ly. Okay? So these are of this form. So we can only have that 0 Lx belongs to G if Lx is also 0. Okay? And so we have reached a contradiction. So this means that our assumption that n was solvable, yeah, which we needed to use to show that S was isomorphic to G, that this assumption is not true, and so this means that n cannot be solvable. Yeah. Hence, yeah, okay, I agree that this is a deeper theorem probably than what I have already been doing, and I promise also that this will be one of the more difficult theorems, so don't give up for next time. So as a conclusion, what I have shown now in this setting is that if G is simple or semi-simple, yeah, then the n cannot be solvable. So this means I can put crosses where I see solvable algebras n. Yeah. So more or less we had abelian nilpotent solvable, then abelian nilpotent, then n could not be simple, semi-simple. Yeah. Other way around, if G is simple or semi-simple, then also n cannot be too easy, being abelian nilpotent or solvable. Okay, tomorrow I will finish up the rest of the table, and then we will see what the conclusion is and what's still to do. Okay, I thank you for your attention for today.
Thank you. Okay, are there any questions, comments, remarks?
They are all dead from the last year.
I don't see anything in the chat. Okay.
Okay, so see you tomorrow.
Thank you.
Okay. Let's thank the speaker again.
Mm-hmm.
They have a question.
I have a question.
Okay.
Yeah.
So when you said about the construction of Post Lie algebra with a direct sum of two Lie algebra.
Yeah.
So my question is, if we don't have a direct sum, can we have the construction of Post Lie algebra?
So even if you cannot write your Lie algebra as a direct sum of two subalgebras, yeah, then there are still other possibilities to construct sometimes Post Lie algebra structures, but I do not know of any general method in this way. And in fact, it's very often possible to write your Lie algebra as a direct sum of two subalgebras. For example, if you take any solvable Lie algebra, yeah, then you know that the derived Lie algebra is smaller than the whole Lie algebra. So this means that you can find an ideal of codimension 1. So you just take, yeah, and then you take this ideal plus a one-dimensional space, which is always a subalgebra, and so you can already start doing this. Yeah.
Okay.
Yeah, and simple ones you can also write like this. So maybe if I would think further, most Lie algebras you can, well, no, not most, but many Lie algebras you can write as a direct sum of two subalgebras. Of course, you cannot reach every possible situation in this way.
Okay. Thank you. Thank you.
You're welcome.
Any other questions? Okay, if not, let's thank Karel again.